In this part, I would like to highlight the differences between two approaches within the context of the discrete element method, the hard sphere and the soft sphere approach. Let us first start with the so-called hard sphere approach. This approach uses Newton's law in the integral form, meaning that we just look at the momenta before and after the collision event. So here you again see this momentum balances, right? It's similar to what we have seen before. However, now Newton's law is now applied to each individual particle indicated by this I, by the subscript I here. That means these equations are satisfied by both particles that collide in our binary collision, right? You again see that there is only one quantity that we have to predict, the momentum exchange Ji, and this is sufficient for both the translational direction and also for the angular component. Details on how to evaluate this momentum exchange are available in literature. We have seen it before. We have directly calculated the collision with other simulation, with the soft simulation. However, if you apply the hard sphere method, this information is not available and you have to predict this momentum exchange term for each particle. Let us now also explain how the hard sphere method works by looking at the collision of four particles. These particles have a higher relative speed, so they will collide first, and these two particles have a lower relative speed, they will collide later. If we now apply the hard sphere method, we can essentially look at what would happen in real time, so what would be reality, right? And what is then the case if we do a so-called hard sphere simulation. So what you have seen now is that the hard sphere method essentially just changes the particle's position and velocities. The velocities are not indicated here, but it's the case. They just change the positions and velocities at the collisional events. That is why the hard sphere method is also called an event-driven simulation or event-driven DEM. Again, for the lower particles, you see here we, at the collision event, essentially change positions and velocities. And of course, we also need to do that for all the other particles. However, we are not so much interested in what happens in between these collision events with the hard sphere method. In contrast to that, let us now look at the so-called soft sphere method or the soft sphere approach within the context of the discrete element method. Here we do something different. Again, let us look at a binary collision. Now it's a heads-on collision, there will be no rotation. And what you see is the particles collide. There is a significant overlap. We allow for this overlap. Of course, this overlap is unphysical because particles don't change their shape, they just overlap. But what you have seen is that, also illustrating why this is called a soft sphere method, the particles are soft, they are squishy and are allowed to overlap. Here we apply Newton's law in the differential form, so the form that is typically taught in high school. Again, we apply it to each individual particle. The subscript I now indicates the particle index. This is the translational momentum. If the mass is constant, which is very often the case, we can pull out the mass from the differential and arrive at this equation. Rarely you also find a formulation like this, where we have replaced the velocity by the derivative of the position of the particle. This is not very often the case. Very important, here on the right hand side we have to just sum up the forces. Similarly for the angular momentum, here you see the Newton's second law for the angular momentum. Again, we can pull out this moment of inertia. Please note that we can only pull that out for spherical particles. In general, this I here, this moment of inertia tensor is really a tensor and non-constant in the global coordinate system. So this is more complicated, but we will go into this detail later on. Again, we can replace here the angular velocity with the time derivative of the angular position. It's not very important here, and it's really done. The important part is, again, we just have to sum up all the torques to calculate these time derivatives, and in short, the soft sphere method relies on a straightforward evaluation of this Newton's second law by computing first forces and torques and then integrating it. The core part about the soft sphere method is, however, that we need to treat the collisions somehow, and the collisional forces, the collisional exchange, momentum exchange, is modeled, and this is the key part, by a spring dashboard element typically. This is the core of the so-called soft sphere DEM method, or simply the DEM method, the classical DEM method. Great. So now let's have a look how these contact forces, the soft sphere contact forces, are modeled. For the spring element that you see here, we use typically a formulation that connects this overlap between the two particles, in our case spheres, with the spring force, and the proportional constant is here K, which is simply a stiffness, has the units Newton per meter, obviously. And in the classical hook model, as it is called, or linear spring model, this is a constant factor that we have to just pick as a user input. You will see later that many other models exist as well, and this is one part of it. The second part of the interaction form, the contact interaction part, is this dashboard element. This is also classically used in the soft sphere DEM. There are other methods as well, as always, and here this dashboard force is modeled as a constant c multiplied by the relative velocity between the two particles. This is the very important difference between soft and hard sphere. In short, the soft sphere method models truly the time evolution of the contact force and is integrating the differential form of Newton's equation of motion. In contrast to that, the hard sphere method is calculating the momentum exchange term J and then doing this event-driven integration of the equations.